The first speaker is Manus Visser from Radboud University in the Netherlands. Take it away.
Yeah, thank you very much. It's really a true honor to speak at this TED Fest. So TED's work has had a deep impact on my scientific thinking and on my career. So thank you for that. And especially these two papers where he derived the Einstein equations from more fundamental principles, which were already mentioned today. And the second paper appeared during my PhD. And I remember meeting Ted for the first time at the Solvay conference in Brussels. And I had read that paper very carefully, worked out all the derivations in the paper, and then asked him a ton of questions. And then we started collaborating actually immediately at the conference already. So I'm very grateful for that. And also for allowing me to work with him and being a great mentor during my PhD, even though I was not his student and we were miles apart. So the third comment I wanted to make is that Ted has the ability to be very critical of his own work. And he's flexible enough to change his mind, which is, I think, a sign of a great physicist. So here are a couple of examples. I don't know if you agree with this, but you started working on loop quantum gravity, but now you're more in the field of string theory or holography. You had these two different derivations of the Einstein equation, so you also sort of switched your mind on that. And actually, even in the first case, you presented it in a different way later on. Then you also changed your mind on the black hole information loss paradox. And then during my PhD, we wrote a paper about causal diamonds having negative temperature. But then a few years later, we changed our mind and we thought, okay, no, the temperature is indeed positive, also for the static patch of de Sitter space. So the minus sign in the first law has a different explanation, and we wrote a paper with Batul and Andy explaining that. So I think this is all very healthy. Okay. But what am I going to talk about? So in your paper from 95, the Einstein equation of state, you say that, well, the Einstein equation is an equation of state. And you explain actually in that paper what an equation of state is. So if you take the Clausius relation and you combine it with the first law, that implies that the temperature follows from the SDE and the pressure follows from T the STV. And you say the latter equation is the equation of state. So the relation for the pressure. However, the pressure is precisely the variable that doesn't appear in gravitational thermodynamics. Whereas you say the Einstein equation is an equation of state, whereas the pressure doesn't really appear in the rest of your paper. So, well, I find that a bit confusing. So I'm going to try to resolve that. But morally, I think it's correct, but that's because there is a more general definition of equation of state, where actually the first equation is also considered to be an equation of state. And I think that first equation is more where you derive the Einstein equation from. So in this talk, I will give a definition of pressure and volume for black holes using so-called quasi-local thermodynamics and interpreting that in a holographic way. So what is the issue here? So if you consider the first law for Schwarzschild black holes, asymptotically flat Schwarzschild black holes, dm is kappa, the surface gravity over 8 pi g, dA, where AH is the horizon area. Well, that's comparable to dE is TdS, but there's no pressure volume term here. And this applies also to other stationary black holes. So for instance, Kerr-Newman, there are work terms, but they are more like chemical potential charge terms, but there's no pressure volume work term. Now, another related question is about extensivity or non-extensivity of black hole entropy. So it is a common place to note that black hole entropy is non-extensive because it scales with the area and not with the volume. But this is kind of ill-defined if we don't have a notion of volume, thermodynamic volume for black holes. So I'm going to give you later a definition of black hole volume, but it's actually quite difficult to define that. So what is extensivity? Well, in thermodynamics, entropy is extensive if it is a homogeneous function of degree 1. So that means that this scaling relation, this homogeneous scaling relation where alpha is positive, is satisfied. And by Euler's theorem for homogeneous functions, or just deriving this equation with respect to alpha, setting alpha equal to 1, you can find the Euler equation. I call this the Euler equation. E is Ts minus PV plus mu n, where T, P, and mu are intensive variables, so they are homogeneous functions of degree 0, and they follow from partial derivatives of the entropy with respect to E, V, and N. And E, S, V, and N are extensive, but only if this scaling relation holds. And this, right, so other people have argued that black hole entropy is non-extensive, namely Landsberg and Trana in 1980, and they said, well, if you consider the black hole entropy for a Kerr-Newman black hole in 4 dimensions, then this is not a homogeneous function of degree 1. If you calculate this, it's just not equal to alpha times S. Although this argument is formally correct, it's not based on a physical notion of extensivity because there's no notion of size here. There's no volume here. So what this scaling relation means is that if you scale the volume, for instance, if you double the volume, then the entropy also doubles. But in this relation, there's no notion of size. In particular, you're just changing the thermodynamic state, but the boundary at which these charges are defined is kept fixed at spatial infinity. So we need a notion of volume or size of the system. Another point I want to make is that extensivity actually only holds in the thermodynamic limit, or I will call this the large system limit. So the large system limit is you take the volume to infinity while keeping the number density fixed. But in our case, for black holes, I don't have a number density, so I'm going to keep the entropy density fixed. And Landsberg called extensivity the 4th law of thermodynamics, but it can be violated, as he was also aware, because he also looked at black holes and stating that it's non-extensive. And for instance, it can be violated away from the large system limit for small thermodynamic systems, and also for self-gravitating systems due to long-range interactions. All right, so we need a notion of volume for black holes, but in general, this is hard to define because in GR, due to diff invariance, there's no preferred slicing. For stationary black holes, you can do a little bit better because you have a stationary killing field outside the horizon, and you can look at slices that are orthogonal to the killing field. So you have some preferred time slices, but inside the event horizon, they are time-like. It is a time-like surface. So for a Schwarzschild black hole, this naive Euclidean volume is really nonsensical because it's defined on a time-like slice. And moreover, or maybe more importantly, this volume is just a function of the horizon radius, but the area or the entropy is already a function of the horizon radius, which means that volume and entropy are not independent in this case. And that's absolutely crucial in thermodynamics, that all your state variables are independent from each other. So volume and entropy have to be independent from each other. So this is not a good definition. Now, there are several other proposals for black hole volume, by Christodoulou and Rovelli, Parikh, Stanford, and Susskind related to complexity, but actually I want to focus on definitions of black hole volume that contribute to a first law, so that have a thermodynamic interpretation and that are also conjugate to a certain pressure. And so there are two examples, two proposals that are quite influential, one by Padmanabhan and one called extended black hole thermodynamics or black hole chemistry, so now I'll review these two proposals in turn briefly. So Padmanabhan's proposal is precisely that this volume is this naive Euclidean volume. And the conjugate pressure is the radial component of the stress energy tensor evaluated at the horizon. And then he reinterprets the radial Einstein equation at the horizon as an equation of states. So, I mean, formally this equation might be right, but I think the interpretation as an equation of state is completely wrong. And then he multiplies this by dV, so V being this equation, and he gets a sort of first law, where E is the Misner-Sharp energy. However, as I said, the entropy and volume are both functions of the horizon radius, so they're not independent. And so in particular, this energy function doesn't really make sense. It's ill-defined. And also partial derivatives are ill-defined because S and V are basically the same variable. Okay. So the other proposal is where you define the pressure as minus the cosmological constant. And this follows because formally you can vary the cosmological constant in the action, and the cosmological constant in the Einstein equation can be interpreted as a perfect fluid contribution to the stress tensor. So if you vary the cosmological constant in the first law for Schwarzschild ADS black holes, you get this extra term. So this equation is formally correct. And then people interpret the conjugate quantity theta or minus theta as the thermodynamic volume, such that this equation now becomes dm is TdS plus V dP, which means that the mass is actually an enthalpy, because enthalpy satisfies dH is TdS plus V dP. Well, this is already very strange because mass in ADS-CFT, for instance, is in general in GR is just the Hamiltonian, so I think it should be the internal energy, not the enthalpy. But there are other problems with this proposal. First of all, for static black holes, so for ADS Schwarzschild, again, this thermodynamic volume is just the naive Euclidean volume. So it just depends on our age. So you have the same degeneracy problem as for Padmanabhan. And secondly, the cosmological constant is not a state variable. It's a coupling constant in the theory. So when you vary the cosmological constant, you're changing the theory, and you're not changing your thermodynamic state. You're not moving from equilibrium state to another equilibrium state. Yeah, but okay, if I just do GR, you can also, okay, there are ways, for instance, including scalar field or something. You can rewrite the cosmological constant as a field as well. But I think another reason why I don't like this state variable thing is that in ADS-CFT, the cosmological constant is related to the central charge. So you're changing the central charge, which really means you're changing the theory, the CFT degrees of freedom. So this is not a normal thermodynamic process. Okay, so now I want to move to a holographic proposal for black hole pressure and volume. And this is based on York's quasi-local gravitational thermodynamics. And actually the holography didn't exist back then, but the holographic interpretation was also just suggested in a paper by Batul and Adgar and Sanjit. And it's inspired by ADS-CFT and its TT bar deformation. So this approach depends on the introduction of a time-like boundary outside your black hole. And it follows, or it's motivated by diff invariance, which dictates that conserved charges and thermodynamic variables in gravity must be codimension 2, must live on codimension 2 surfaces. And my claim is that this should apply as well to black hole pressure and volume. And secondly, I'm going to use the holographic principle. So I'm going to assume that there is a duality between a gravitational theory inside this boundary and a non-gravitational quantum theory on the boundary. Now, the proposal is that black hole volume and pressure should be defined holographically, so on this boundary, as the spatial volume and thermodynamic pressure of the dual theory. And so York, in this famous work, derived a quasi-local first law for Schwarzschild black holes. So if you introduce a time-like boundary, then you get an extra term in the first law, which is a surface pressure and the area of your time-like boundary, of a cross-section of your boundary. And E is the quasi-local energy. Now, in the dual theory, you use this dictionary. The surface pressure is related to the thermodynamic pressure and the area to the volume. And then you get this, so through this trivial dictionary, you get a standard thermodynamic first law. And this is, of course, we're going to use this to study extensivity. So here are the definitions of the quantities that appear in the quasi-local first law. So you can imagine that I have this time-like boundary sitting at a constant R surface. So it's like a spherical cavity. So most of these, so the energy is defined as projections of the Brown-York stress tensor. Similarly for the surface pressure. And the temperature is the redshifted Hawking temperature, so which is the Tolman temperature. And crucially, in this first law, the entropy is independent from this area. So the entropy is the horizon area proportional to the horizon area of the black hole, and the area is A is the area of the boundary. So you actually have to regularize these quantities, especially the energy and the surface pressure, because they diverge when you take R to infinity. So what we do is we do a background subtraction. But in ADS, you can also introduce counter terms. And then for Schwarzschild black holes in 4D, you get these types of expressions. And they satisfy this quasi-local SMAR relation. So they're related in this way. And York showed that there are actually two real positive solutions. If you fix the temperature and the area or radius of the boundary, then there are two solutions for the horizon radius, which are the small and large black holes. So famously, the large black hole is thermally stable, but is actually mechanically unstable, whereas the small black hole is thermally unstable, but mechanically stable. Okay. Now, an aside on some formal, or relatively formal equilibrium thermodynamics. So Cullen, in his textbook, defines so-called thermodynamic representation, which you can think of as the thermodynamic analog of statistical ensemble. So it corresponds to a choice of thermodynamic potential and a choice of independent state variables. And then a fundamental relation expresses the potential as a function of these independent variables. And different potentials are related by Legendre transformations. So for instance, in the energy representation, S and V are independent, and the internal energy is the potential. In the canonical or Helmholtz representation, T and V are independent, and F is the potential. Now, you can define equations of state, that's why I'm writing the slides, as the functional relations between the conjugate variables, so in this case T and P, and how they depend on the independent variables. So in the energy representation, the equations of state are the functions T as a function of S and V, and P as a function of S and V. But each representation has different equations of state because it has different independent variables. So as I said in the beginning, just saying that P as a function of T and V is the equation of state, which you often see in textbooks, and which Ted also wrote in this paper, is that's only one equation of state. Actually, there are multiple. So this is the other one in this representation, and then in another representation, you have other equations of state. So you can find these equations of state for a Schwarzschild black hole as well, explicitly. Maybe I shouldn't go into this, but in the energy representation, you can find T as a function of S and V, and P as a function of S and V. And in the canonical representation, where there are two branches, you can also find these equations of state. And for instance, this is a plot of P as a function of T and R, or P, where you see these two black hole branches explicitly. Okay, so now I want to study extensivity for Schwarzschild black holes. And as I said, this might depend on the thermodynamic representation. So in the energy representation, where S and V are independent, you can write down the potential, which is the Brown-York energy, and it satisfies a quasi-homogeneous scaling relation. So in these space and dimensions is this formula, and this implies, via Euler's theorem for homogeneous functions, implies this quasi-local Smar relation. Now, this differs from the Euler relation, E is Ts minus PV, because of these dimension-dependent factors, and this means that E and S and V are not extensive, and T and P are not intensive. And this also follows from the large system limits, where you take V to infinity while keeping the entropy density fixed. You can find that the energy density actually vanishes, which means that the energy is sub-extensive. So Schwarzschild black holes are, in this formalism, sub-extensive in the energy representation. Now, in the canonical representation, the large system limit is a different limit. You have V and T as independent variables, so you send V to infinity, but T you keep fixed. And then extensivity actually depends on the branch in this representation. So for small black holes, the free energy is sub-extensive in the large volume limit. So the free energy density vanishes, and similarly the entropy and energy also vanish in the limit. Whereas for large black holes, the free energy is extensive in the large volume limit. So the free energy density just has a finite limit. Similarly, the entropy density also has a finite limit, but the energy density does not. So this is reminiscent of the previous energy representation, where we saw that the energy is sub-extensive. And you also find that in the other representation. So this means that extensivity is a representation-dependent quantity. So in the canonical representation, it's extensive for large black holes, and here it's not extensive, but it's also branch-dependent, because for small black holes it's sub-extensive, whereas for large black holes it is extensive. Now, you can also do this for ADS-Schwarzschild black holes. So in the energy representation, in this case, you find that extensivity is restored in the large volume limit due to the presence of a cosmological constant. And this you can understand from the SMAR relation. So we derived a quasi-local SMAR relation for ADS black holes, where you have this extra term, which is proportional to the cosmological constant. And V tilde here is what we call a background subtracted killing volume, which appeared in earlier work, which Ted and I defined in earlier work. But now, what's wrong?
Sorry, I'm not sharing the slide.
Okay. Well, that's a bit too late. I don't know how many people are following on online.
You can find out.
Yeah, the screen is very large. So.
Sorry about that.
Okay, so we have this SMAR relation for ADS black holes, so quasi-local SMAR relation, where this quantity might be unfamiliar, but it's defined in this way. So it follows from background subtraction. So this is well, the killing vector field, stationary killing vector field, interior product with the volume form. But that's actually divergent if you integrate it over this spatial slice from the horizon to spatial infinity. But if you subtract this quantity, where this is the lapse in the black hole spacetime and this is the lapse in the background ADS, pure ADS spacetime, then this is finite. And this is just DDT in pure ADS, and this is the volume form in pure ADS. So this is a bit of an extension of what Ted and I did back in 2019, because in that paper we derived the SMAR relation for ADS black holes, where you take this boundary to infinity. So this term was not there. Yeah.
You derive the counter.
Yeah, you can also do it in that way, but we in this formula we did it using background subtraction, but you can also use
And it shows up
renormalization. Yes, we didn't do that, but you could use holographic renormalization, introduce counter terms, and then that will appear in E, P, and also in this P. So it will have a slightly different expression. Yeah. Now, you can take the large volume limit in the same way, so V to infinity with fixed entropy density, and then this SMAR relation turns into the Euler relation. So extensivity is in that case restored, but this is not the CFT energy, because we've taken a different limit. If you would take V to infinity while keeping S fixed, so in this case, S is actually going to infinity as well, right? Because I keep the entropy density fixed, send the volume to infinity, which means that S also goes to infinity. The CFT limit is where you take V to infinity at fixed S, and then you get CFT energy, and you can also get the CFT pressure equation of states, and you also get the Euler equation for a CFT. But this is a different limit where you get an extensive energy, and you can see explicitly that it is extensive because it is proportional to volume and it only depends on entropy density. So if I rescale all these quantities with alpha, E also scales with alpha linearly. but it's a sort of funny limit, which is so it's not a CFT limit. And it shows that for ADS black holes, the energy is actually extensive in this large system limit. Now, you can also do the canonical representation. I didn't have a slide on it because it's quite similar to the one for asymptotically flat Schwarzschild black holes. So you can take the large volume limit and show that the free energy for small black holes is sub-extensive, whereas for large black holes, the free energy is extensive. There's one difference, one tiny difference, is that in this case, the energy is also extensive, because in the energy representation, it's also extensive. Whereas here, the energy was sub-extensive for large black holes in the large volume limit. So that's one tiny difference. Okay, so actually, I can conclude now. So we argued that black hole pressure and volume should be defined holographically via quasi-local gravitational thermodynamics. And we showed that for in the energy representation, Schwarzschild black holes are non-extensive. Right, that was this part. So they are the energy is non-extensive, and hence the entropy as well. And this non-extensivity usually appears in theories that are non-local. So this suggests that the holographic dual theory on this time-like boundary for asymptotically flat spacetime is non-local. Now, some future directions, we only considered the simplest black holes, uncharged and non-rotating black holes, but you could extend this possibly to charged and rotating black holes. However, for rotating black holes, you cannot use this background subtraction because you cannot embed it in you cannot embed this boundary globally, I think, in Minkowski spacetime. So maybe you have to work locally or something. Not sure yet. Then a second direction that I had in mind is that I just considered equilibrium thermodynamics, but using the membrane paradigm, you could perhaps find a hydrodynamic description of gravity on a general time-like boundary. So the membrane paradigm is usually defined near the horizon, and the fluid gravity correspondence is defined at infinity, but you could define sort of a membrane paradigm, an interpolating membrane paradigm between the horizon and infinity that holds at every time-like boundary. And then the story I told you today is just a very special case of that, where you have a global equilibrium state, whereas in this case, quantities are defined locally, it's not equilibrium, and you can have viscosities, and etc. And finally, another thing I'm interested in is heat engines. So I defined pressure and volume. So now I can make actually a cycle, thermodynamic cycle in a PV diagram and construct all kinds of heat engines like Carnot, Stirling, Otto, Diesel, etc. So I actually have a paper already on heat engines in ADS CFT, where we construct heat engines in the CFT dual to ADS Schwarzschild black holes. But now with the definition of pressure and volume also for asymptotically flat spacetime, you could imagine constructing heat engines in this dual theory on this boundary that use the thermodynamics of black holes, or I can use the dictionary for thermodynamics of black holes, but they are they are defined in the boundary theory, and then I can compute all kinds of I can compute the efficiency for all kinds of heat engines. So you can have like an isotherm and an adiabat, or an isotherm and an isobar. So you can have different kinds of cycles that define different heat engines and that have different efficiencies. Right, so that is an interesting future direction. I should also emphasize that this pressure and volume that we defined applies both to Schwarzschild, to asymptotically flat, and to anti-de Sitter Schwarzschild black holes, whereas the other proposal that I mentioned in the pressure and volume actually only applied either to asymptotically flat or to ADS black holes. So with that, I'll thank you for your attention.
Okay, thanks very much, Manus. We have plenty of time for questions. I'll get my steps now.
So I'm confused about something very basic here, which probably means that I'm just missing something.
Yeah.
The black hole entropy is proportional to the area of the horizon. So in your extensive case, where the ratio of entropy to volume remains finite, does that mean that your volume is scaling as the area? How does that work? Is it that as you increase the volume, you're considering black holes with larger areas, or?
Yeah, that's right. So
Okay.
in this limit, I take v to infinity and s to infinity such that their ratio is fixed. So they are proportional to each other, but they are both very large.
Okay, so you're not talking about a fixed black hole
Correct.
anymore. You're talking about a thermodynamic system in which you vary what black hole you're talking
Yeah.
about.
And that's
Okay.
what you would call the large system limit. Because for a gas, you could take the volume to infinity, but you also want to take the number of particles to infinity such that your system sort of stays the same. Otherwise, your entropy just decreases.
Okay.
Other questions?
You made a comment about the rotating black holes
Yeah.
at the end. You said there was like a challenge getting a counter term, is that right? Or the vacuum subtraction?
Yeah, the vacuum subtraction, I don't think that works. You cannot embed this boundary in Minkowski.
Okay, so
So-
yeah, the question was, can you use this Mann-Merolf counter term method and basically do holographic renormalization, but in flat space? They have this way of writing down these intrinsic counter terms there.
Yeah, that would be great. Although I talked to Mann and he didn't mention this, so
Oh.
I'm not sure. Maybe
Maybe
done
Could
done
comment.
things.
It's designed to give you a finite action for asymptotically flat things. So when you've got the full infinite solution and your boundary is, quote, at infinity, it should work fine. I did have the impression, though, that you really wanted to work with finite cutoffs and studied that limit, so you might need some generalization.
Yeah, but the real issue is that you want to get rid of the divergences at infinity because
That did the job just fine.
yeah, so then I think I can use it. Yeah, and it works for rotating black holes as well. Yeah, yeah. Okay, thanks for the suggestion.
Yeah, could you expand a little bit on these heat engines? So my naive picture of a heat engine is I have a hot reservoir and a cold reservoir, and I want to extract work from the heat flowing from one to the other. But where are the reservoirs and what's the heat flow, and in what sense what is it the efficiency of that you're calculating?
It's efficiency of the black hole space-time, I would say, but I think the exterior to the boundary, those are the heat paths, but then I have to separate the hot and the cold, right? So I need two heat paths, one that pumps in heat and one that is like a sink.
I see. So the boundary is like the engine, and
Yes.
you imagine heat can flow into it and out of it
Yes.
to a colder reservoir.
Yes, indeed.
Is there any, okay, so is there a physical, can you do you think of that as purely a formal thing, or can you imagine some kind of actual extraction? I mean, I was trying to think, does this involve mining the black hole atmosphere, or is there any even just far out thought experiment you could do where you would realize this heat engine?
Yeah, I have to think about that more. I think about it more formally as like, okay, I have my boundary theory, which is my engine, and then I couple it to reservoirs. That doesn't really matter what those are, as long as they're large enough such that their temperature is fixed. But you want something more like a process in the black hole space-time.
Well, yeah, or maybe actually just, I guess we could think about the boundary theory just actually being a physical system, which happens to be dual to a space-time description.
Yeah, that's how I thought about it in the ADS-CFT case. Like I just have some gas that maybe acts like maybe massless photons that are CFT, and then maybe it has some dual description if it's strongly coupled and has large number of degrees of freedom. And then I can couple that to heat baths and do experiments with it and make an engine, calculate the efficiency. That's how I thought about it in the CFT case. But in the bulk, I don't have like a physical process, like lowering a box or something.
Yeah. Okay. Thanks.
Other questions? Go ahead.
Can you go to the small versus large black hole extensivity slide? I would think, yeah, with T fixed, I would think that like the small black hole is subdominant anyway, thermodynamically. So is this even relevant to talk about extensivity of that phase?
Yeah, I mean, in a statistical ensemble, it would be subdominant, but here I agree with that. But I mean, I can consider that branch, right? I mean, I think it's this branch. And then I can ask, is this branch in a certain limit extensive or not? And it's always sub-extensive. So it's sort of interesting that it is the subdominant, unstable, and also sub-extensive, but mechanically stable, actually. Yeah. And actually, I was surprised that the large black hole is extensive. I would actually expected it to be sub-extensive, which is also what you had in your paper.
Yeah. I had a question related to what I was talking about in the case of Einstein. So the very general level, right, you could think about what you're doing here as trying to get a handle on quantum gravity by applying like thermodynamics to black holes and take that very seriously. And so likewise, Einstein was trying to get a handle on like, the quantum nature of electromagnetic fields by applying thermodynamics, particularly like, notions like temperature and entropy to electromagnetic fields, which was quite controversial at the time, right? So when Dean first started doing this, like Helmholtz says, this is thermodynamics gone mad. And so, listening further to this, like, like the preparing my talk, the most interesting thing I found was that Einstein decided that Bose-Einstein statistics is preferable, not because like he had some idea about like particles being indistinguishable, because it gave like an entropy that had the proper thermodynamic behavior, right? And so like yours, I mean, like it seems that, like on a general level, you're doing very similar things. So my question is like, do you find it helpful? I mean, I could think of this as using this as propaganda for this approach. Like, look, string theorists like to point to like the late Einstein, thinking beautiful mathematical ideas that never got him anywhere. You could point to like, well, like when Einstein was doing like the stuff that he's now famous for, like he's actually doing something similar to this. Is that appealing, or is this just like sort of my parochial way of looking at the world?
I don't want to compare myself, but that's definitely how my perspective as well. And so that's also why I said that at the end that thermodynamic description tells us something about the dual theory, like it's non-local, for instance, and any dual theory or a concrete microscopic theory that you write down should satisfy, for instance, these equations of state, which are very specific. Like it's very difficult to come up with a microscopic system that satisfies these equations of state. Right, they're very detailed. And so this kind of detailed thermodynamics tells us something about the underlying microscopics. But we don't have that for asymptotically flat Schwarzschild black holes. Whereas for ADS-CFT, we have a better handle on the microscopic description. Yeah.
Okay, one last question if anybody has one. Okay, no. Okay, we're going to coffee break. Let's thank Manus again. We're coming back at